Hi everyone. The purpose of this video is going to be to go over how I determine the different graphical features of an exponential function. So if we look at this example, we can see that I was given a function f of x equals 2 to the x, and I've already gone ahead and drawn out a sketch of that. If you're not sure how to do that, I've made another video on that, so you can go ahead and look at the video on graphing exponential functions. But for this one, we're just focusing on pointing out the key features. So if you look to the right, there's a list of all these different key features that you might be asked to determine. You'll find domain, range, end behavior, y-intercept, and asymptote. The key features here that are probably newer to you are end behavior and asymptote. And you can see that I have the asymptote listed at the bottom of this list, but I'm actually going to give you guys a hint right now, and that is to always start by finding the asymptote, and then that will make the rest of your life so much easier. So remember that an asymptote is just a line that my function approaches but never crosses. And as I've shared previously, when working with exponential functions, there is always going to be a horizontal asymptote. So there's never going to be a vertical asymptote. There's not going to be a slant or diagonal version asymptote. There's going to be a horizontal asymptote. And that means it's just a line that goes left to right. If you forget what the word horizontal means, you can think about the horizon. Like if the sun is rising over the horizon, like the horizon is just like essentially the end of Earth. Not that Earth ends. I don't know, I'm explaining that bad, but I'm not a science teacher. So, but yeah, basically it's flat when you're looking at the horizon. So, moving on. This is going to be a flat line going left to right that the graph approaches but never crosses. You will notice that that occurs in exponential functions because with exponential growth, you start out very flat and then you start increasing quickly. With exponential decay, you start out decreasing really quickly and then you sort of flatten out towards the end of the graph. But either way, there's one portion of the graph that is very flat. And that is the part you're going to look at when you're trying to figure out what is the asymptote. So if you look at the left side of this graph, you can see that I had a couple points where x was 3 and x was 2 that I plotted onto this chart, where basically when I plugged in those x values, I got really, really small y values. One of them was 0.0125 and one was 0.25. But basically, those numbers are getting smaller and smaller. And as I move further left on the graph, it's just going to keep getting smaller and smaller. But no matter what x value I plug in, I'm never going to actually get a negative value out. And the reason being is this function here, no matter what I put in an exponent, that isn't going to actually give me an output of a negative number. So I could put negative 2 to the 10. But remember that a negative exponent just means 1 over the number to the exponent. So like 1 over 2 to the 10. I don't even know off the top of my head what 2 to the 10 is, but it's something in, I don't know, 512 maybe, or 1024, something like that. So 1 over a really big number is going to give you essentially 0. Not quite, but it's certainly not going to give you a negative number. So we're never going to get into the negative numbers. We're never going to cross below 0. And so what that tells me, because these numbers are getting really, really, really close to 0, but not quite getting to 0, that tells me that that is an asymptote. So I'm going to draw that in with a dotted line. I'm drawing it right underneath the x-axis. You will see this drawn like this sometimes because if you draw it right on the x-axis, unfortunately, you probably won't be able to see it. So we sometimes draw it right underneath, but know that that line is representing a horizontal asymptote of the x-axis. Now, when it comes to writing the equation for a horizontal asymptote, I am always going to have it be of the form y equals some number. The reason that that is the case is because a horizontal line always has the same y value. If you think about this line, like this line is the x-axis. So if you look on the left of it, it's going to have a different x value. You'd have negative x values on the left side. You'd have positive x values on the right side. There's a bunch of different x values. But because it's a horizontal line and it only goes from side to side and not up or down, the y value never changes. It never goes to another value on the y-axis. So the equation of this line is going to be y equals 0. Okay. And now that we've finished talking about the asymptote, we can go ahead and find the other features. And for some of them, it's going to be a lot easier now that we already know the asymptote. So what I'm going to do now is I'm going to look at domain and range. These are definitely things that we've talked about plenty before. Domain is basically the set of all x values in my function, and the range is the set of all y values. So when it comes to domain, I'm looking for the x values. I'm looking for how far left and how far right does my graph go. Remember, we also always read the graph from left to right. When I look at the far left side of this graph, I see that there is an arrow pointed out towards the left. That means that this function continues forever in that direction. And as we know by this point, that is the negative x direction. So as I keep going forever and ever in that direction, I'm going to have negative infinity. When I look at the rightmost part of this graph, you see an arrow that is pointed mostly up, but it's also pointed slightly to the right. And what that means is that as it increases, it's going to go higher and higher and higher, but it will also always be moving slightly to the right. So since it will forever be moving in the right direction, it will eventually get to positive infinity. And as I've mentioned before in class, the domain of every exponential function will be negative infinity to infinity, because it is a continuous function. The next thing that we're going to look at is the range. So the range is the set of all y values that you could get with this function. And so we've already talked about a little bit of a limit in this factor because we've talked about how this function will approach an asymptote and never cross it. So when we look at range, we talk about, okay, I'm reading the graph from bottom to the top. Where does the graph start? And you'll notice that none of the graph falls into those two quadrants on the bottom side of the graph. Nothing's in quadrant 3 or 4. So what that tells me is that the y value is never going to be negative, and I'm never going to go below the x-axis. Since the asymptote is at y equals 0, the smallest y value is going to be like approaching 0, but it's going to be just above 0. So basically, looking from bottom to top, I see this function start around 0. And then as I keep looking up, I see that arrow pointing up, and it goes up and increases forever, which gives me infinity. Just to go back to that 0 part again, you will notice that I used a parenthesis here, not a bracket. You'll know from previous lessons that a bracket means inclusive. It means that that number is a part of the domain or a part of the range. Because an asymptote is never actually touched by the function, my function never actually gets to 0. So 0 is not included in the range. The reason we use 0 as the starting point is because the function starts so close to 0. It's like as small as you can imagine, 0.000000001, right? Like that's when the actual range begins. So what we just say is we say it starts at 0 non-inclusive. So basically it doesn't include actually 0, but it includes the next closest thing. Yeah. Now that we've done domain and range, we're going to talk about end behavior. And so this is new for this type of function. And I want you guys to be very careful when you're looking at this. Please don't try to just memorize like what I'm saying and just apply it to everything. Try to think about this logically and actually think about the words I'm saying. And one thing that's going to be important is that you understand what this arrow means. So when you see an arrow, when it comes to this end behavior, that means the same as approaches. So when I read it out loud, I'm going to say approaches. So for this first line of the end behavior, this says, as x approaches infinity, f of x approaches blank. So let's think about what this means. Well, as x approaches infinity, well, x gets bigger and bigger off towards the right side of the graph, right? And infinity would be as far right as you can possibly go. And this is talking about end behavior. So it is talking about what is happening with this graph at the two different ends, one at the left end and one at the right end. Because this says as x goes to positive infinity, I know this is referring to the right end of the graph. And again, please don't just memorize like, oh, it's right and then left. Be careful because you're not always going to see it in this order, right? You might see as x goes to infinity first, but sometimes we might ask you as y goes to negative infinity first. So do be careful about just knowing that you're actually understanding this stuff instead of simply blindly trying to memorize in order. But so this is referring to the right side of the graph, right? As x goes to positive infinity and way over to the right. So at the furthest right point of this graph, what is happening with the function? Well, over to the right here, I'm kind of highlighting in blue, you can see how it's going up, 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 up towards infinity. So what is happening is my function over on this end of the graph is approaching infinity. And that's why we call it end behavior. On the right end of the graph, my function approaches infinity. If you're getting confused by this notation where it says f of x approaches, remember that f of x is the same thing as y. So when I write a function in function notation, it says f of x, and that's just telling me my function using x as the variable. But I could rewrite this same function as just y equals 2 to the x. That is the type of equation you might have seen a lot prior to this class. So f of x and y are essentially interchangeable. They mean the same thing. So you can think about the fact that as I go towards the right of my graph, y is going to be approaching infinity. The other part we're going to talk about is the end behavior on the other side of the graph. So this next one says as x approaches negative infinity. If we think about where negative infinity would be, negative infinity is going to be on the side where values are negative. And so the side with negative x values is going to be on the left side. So this is asking me to talk about the end behavior on the left side of the graph. When I look to the left side of the graph, I see this arrow that points pretty much straight out left. And remember, we already drew in an asymptote here. So if this arrow, it's right above the asymptote and it's just sort of going flat, well, what's happening here is, again, the graph is approaching that asymptote, but it isn't ever going to touch it. So it gets stopped basically by the asymptote. But I'm looking for what value the function is approaching on the left side. Well, it is approaching that asymptote. So it is approaching 0, since 0 is the asymptote. Yeah. So hopefully that made sense. The last piece here is asking for the y-intercept. The y-intercept here is, you're going to find it the same way as any other function. So whether it's like a linear function that you guys learned about in Algebra 1 or any other function that we'll learn about this year, the y-intercept is just where does my function cross the y-axis. So looking at this graphically, I can just see that that place is right here where I'm now darkening in blue, and that happens to be at the point 0, 1 in this function. So that is the y-intercept. If you were ever looking at a function and you can't really see where it crosses the y-intercept by the graph, you can also use the actual function. Know that the y-axis, that's when x is equal to 0, right? The x value of a y-intercept is always going to be 0. So I can also just plug in 0 to my function to figure out what the y value will be. And if I do that, 2 to the 0 would give me 1. So I know that my y value would be 1 while my x value is 0. So that gives me the same thing as what I did over here to the right when I found 0, 1 as my y-intercept. Okay. So I'm going to go through maybe one more example. This one, this is going to have basically the same information. Okay, yeah, I'll do one. Yeah, I'll do a function like this. I'm going to graph this pretty quickly and without explaining what I'm doing, just because, again, graphing is a different video. But if you have questions on that, again, go see that video. I'm trying to just show you guys here as quickly as I can the graphical features. So give me just a moment. Okay, so that is what this function looks like. What I just did really quickly in my head is I plugged in about 5 different x values into this function just to get me some points so that I could connect them. But again, if you want to know how to do that, watch that video. Just like last time, I'm going to suggest that we make sure we are going to start by identifying the asymptote. So again, that is the line that this function approaches but never crosses. So if you'll notice, there haven't really been any transformations of this function. If that's the case, if you just have your base to the x power, you're pretty much always going to have the same asymptote. The only thing that would change the asymptote really is if you are translating your function up or down, right? So if you added a 2 out here, or if you were to subtract your 2, because you're moving the function up or down by 2 units, it would also move your asymptote up or down by 2 units. So your asymptote moves by the same amount that your function translates up or down. Just to let y'all know that real quick, because some of you might be curious as to why you're getting the same asymptote here as we did on the last one. But basically, if you look at this function, you can see that once again, we have this asymptote right here at the x-axis. So I'm going to draw that in. And once again, that gives me an equation of y equals 0 because the x-axis has that equation. The y value on that line is always going to be 0. Now that we've done the asymptote, we can talk about the domain. So the domain here, again, I'm looking from left to right. So over at the left side of my graph, I have this arrow that's pointing both up and to the left. So if it is an arrow pointing to the left, it tells me it continues forever in that left direction. That means it started way, way long ago at negative infinity. Now I'm going to look to the right of the graph. And on the right of the graph, I see an arrow pointed basically straight to the right. So that tells me it's going to continue forever in that direction towards positive infinity. Okay. Now we're going to talk about my range. So again, that is y values. So I'm looking from the bottom of the graph all the way to the top. So again, you don't see the function happening at the bottom here. There's nothing under the x-axis. So I do not start until right after that asymptote. So basically the asymptote at 0 starts my function off. And then as I continue up, 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 my function just keeps going and going and going all the way up to infinity. You will notice that the domain and range are the same here as they were in the last function. Again, that's because, well, I have a different base. I haven't really transformed the function. So my graph looks a little bit different here because it's a decay instead of a growth, but the range and domain end up the same. But regardless of what the graph looks like, the thought process I just explained, that will work to find your different domain or range. I mean, the domain's always going to be the same, but the range will change. Moving on to talk about end behavior though. Remember that I need to read this carefully, so I'm thinking in my brain, as x approaches infinity, what side of the graph does x approach positive infinity? Well, x is positive on the right, so that's talking about the right end behavior. So what is happening on the right side of this graph? Well, again, I have this arrow at the end of the function that's telling me I'm basically going like straight to the right forever. I'm not ever going to actually cross that asymptote, but I am approaching the asymptote on the right side of the graph. So since on that side of the graph I'm approaching the asymptote, I am approaching the y value of 0. Next, I'll look at this next line. It says as x approaches negative infinity. So like which side of the graph do I have negative x values? Well, x gets negative on the left side of the graph, so this is asking me about the left end behavior. And when I look at my function, on the leftmost side of the graph, I see this arrow pointing pretty much up. So that means that my function, the y values of my function, remember f of x and y are the same thing, they are going to go the whole way to infinity because this function just goes up forever on this side. Okay, and then last but not least, y-intercept. Once again, I can find that on the graph. I'm looking here. It is, in fact, the same y-intercept. So the y-intercept is 0, 1. Okay, hopefully that was helpful. Went through 2 examples. Again, not all the examples are going to have as similar answers as this did to the other one. But again, those thought processes I explained will work on any of these problems. So hopefully at this point you feel good to go. Let me know if you have any questions.